So we'll wait for one more minute, let people join, then we'll start. Okay, I think almost everyone has joined. Cool. Guys, are you ready? So we start. So you're not ready? Hello. Are you guys ready? At last. Okay. So last class we were talking about geometrical isomerism. So many of you were not there. Only 3 students were there. But still, right? You will be able to catch up, right? If you have time. Obviously, the yesterday's video was recorded. Please go through it, right? So we already know the gist of it. You definitely studied in your 11th class about geometrical isomerism, and trans, right? So we just saw some insight, like some in-depth problems, in-depth solutions we saw, right? Right. So people, when I told you that one of the conditions required for geometrical isomerism is to have a double bond, right? It is not necessarily the case, right? Now, because at the end of the class, I told you, even if you don't have a double bond, right? Even if you don't have a C double bond C, I can have geometrical isomerism, right? So in which cases, right? So please understand that in all ring structures, right? In all ring structures, it is possible. That is, in all ring structures, geometric isomerism can be incorporated, right? So how? We'll see, right? So now, say for example, I take. Oh my God, second people. Okay, so if I take any ring structure for that matter, right? So you know that each carbon atom is going to have 2 hydrogens attached to it. Isn't it? Yes, any doubts? Okay, right. So if you look at any of the carbon atom, right, you will see that there are 2 hydrogen atoms attached to it, right? So if you look at how these hydrogen atoms are oriented, right? So this is how they're going to get oriented. So you will see that there are going to be 2 bonds for each of these carbon atoms. Say one of the bond will be going inside the plane, right? And another bond will be coming towards you, right? This is going to happen for all the uh, 6 carbon atoms here, right? So please understand, hope you remember the representations. If I put a dashed structure, that means it is going inside the plane. If I put a wedge, it is coming towards you, right? Okay, so please understand that all these 6 carbon atoms will have 2 hydrogens, one pointing towards you and one pointing away from me, right? Okay, now if I have only hydrogens, no, it is not possible, right? It is not possible to have geometrical isomerism. But if I have 2 substituents or 2 of the carbon atoms, right? If I put one methyl group in the first carbon atom another methyl group in the second carbon atom, right? Yes, if I have substituents, ring substituents in the ring, right, I can have geometrical isomerism. For example, right, now if I write 1, 2 dimethyl cyclohexane, right? If I write 1, 2 dimethyl cyclohexane, if I write this compound, like I generally what we do, we write it like this. I put one methyl group here, another methyl group here. This is how we write it, isn't it? But this doesn't show the 3D arrangement like how I showed in the previous case. Correct? Right? So now I will be able to give you a little more insight if I tell that whether it is going to be cis or trans. Right? Now, how will I incorporate it here? Right? Now, very, very simple. Right? So if I tell you it is cis 1, 2 dimethyl cyclohexane, right? Now, this is how you will write it. Right? How will you write it? Now, please understand when I say cis, it should be on the same side. Correct? When I say cis, it should be on the same side. Now, you can when I say cis 1, 2 dimethyl cyclohexane, the two methyl groups, both of them should either point towards you, both of them, or both of them should point away from me. Either of two cases, right? So one of the possibilities which I can write is, say I put the methyl group pointing away from me in this carbon atom. If you put it like that, in the second carbon atom also, you should put it away from me. That means you are going to put the methyl group like this. Or both of them are pointing away, right? So both of them are in the wedge or both of them are in the dash form. This is what is my cis 1, 2 dimethyl cyclohexane, right? Now, can you guess how trans would be?
One methyl group will be pointing towards us.
And other group?
It will be away from us.
Exactly, right? So now cis is same side, trans is opposite side. So for the same compound, if I write trans 1, 2 dimethyl cyclohexane, this is how it is going to look. I'll write it here, right? Say if I put one methyl group pointing away from me, the other one should point towards you. So I have methyl group here, right? So this is how we go for geometrical isomerism in ring structures. Very simple, right? Now one, obviously, you just don't have to know that the hydrogen atoms are going to be like this. 1 point in each of the carbon atom, I have two hydrogen, one pointing away, one pointing towards you, right? So now because of that, because of this pointing away and pointing towards, I can have different orientations of atoms in 3D space, and that's exactly what we are doing here, right? So cis means either both of them are pointing away and both of them are pointing towards me, and in trans, one of them pointing away, one of them pointing towards me. Okay, now what if I have three substituents? Right, say I have one more alcohol, one more OH in say in here. I have one more alcohol coming here. At that time, how will you speak? Right. Now you cannot take all of them together in what one? Oops, something happened. Guys, are you able to hear?
Yes, sir.
Yes, sir.
Thank you. So what I was telling? So if I have one more third substituent, right? So you cannot take all of them together and speak. You can take two at a time and speak. Say for example, if I put, I'll take this as an example. This will give me a better picture. Say if I put OH pointing away from me, right? If I put OH pointing away from me. So as I said, you will not be able to speak all of them, speak with respect to all of them together. You have to take two at a time and speak. So how will I speak? So if I compare this methyl group and this OH, right, I will say that they are cis to each other because both of them are pointing away, right? But if I take this methyl group and this OH and if I compare, they are trans to each other. So hope you understand what I'm trying to say. If at all you have only two substituents, no problem, right? If you have more than one substituent, more than two substituents, three substituents, four substituents if you have, right? You have to take two at a time and then speak whether they are both, whether they're opposite or they are on the same side. Now in this case, this methyl group and this OH are cis, this OH and this CH3 are trans to each other, right? Okay, so this is how I'll be able to speak, what to say, in ring structures, geometrical isomers. Cool, right? Fine. So let me do a problem based on this, right? Please take down the question. Yeah. How many different stereoisomers? How many different stereoisomers exist for how many different stereoisomers exist for this compound, which I'm going to write on the board. For 1 chloro 2 3 chlorocyclobutyl 3 chlorocyclobutyl ethene, right? So for this compound, 1 chloro 2 in brackets, I have 3 chlorocyclobutyl ethene. How many different stereoisomers are existing? That's what they're asking. Okay. Have you ever seen this kind of naming, putting in brackets? Have you ever seen?
Yes, sir.
You have seen it? Good. What does that mean?
So it's branched, sir. It's branched, and the substituent is you have to name the substituent as well. The substituent isn't a simple methyl group or chloro group.
Ah, correct. So in simple words, if I have to put it, it's a branch and that is having a branch. So
Yes.
only in that case, you will be using this kind of brackets, right? So anyways, you try. Okay. How many of you don't know? That's the main question should I ask, right? Tell me. How many of you don't know how to write the structure for this name?
I don't know, sir.
Ah, good. Okay. Anybody else?
I think I can try, sir.
Yeah, fine. I'll give you 1 minute for you to write the structure. Then again, obviously, then we'll go for the questions. Try draw the structure first. Okay. So hope you would have tried, right? So this is how I draw the structure. So you can look at this is going to be ethene, right? So let me draw first 1C double bond C. Okay. Now they say that in the first carbon atom I have a chlorine. Okay, no problem, right? Now in the second carbon atom I have this group, that is 3 chlorocyclobutyl, right? Okay. Now this is how I'm going to draw. So in the second carbon atom, so what you see is there is going to be a cyclobutyl group. No problem. But that is not it. They are telling in the cyclobutyl group, the third carbon atom is having a chlorine. Right? Third carbon atom is having a chlorine. So please understand, whenever you are going to do this kind of structures, that is a branch, this is already a branch, cyclobutyl group is already a branch. Inside that I still have a branch, that is my chlorine, right? So you please understand that only at that time I'll be using this brackets. Okay. So now how will you how will you count the number of carbon atoms? You should always start counting from the main branch. In the sense, say for this carbon atom, this is the branch, so you have to always start 1 here, wherever the branch is starting. Okay, so 1, 2, 3. So 1, 2, 3. In the third position, you have a chlorine atom. Okay, so in the third position, I have a Cl. This is what is the structure. Obviously, I have hydrogens, no doubt about it. right? Okay. Now, is everybody understood how the structure is? Please
Yes,
give me yes.
Yes, sir.
Okay, cool. Right? Yeah. So this is how we draw the structure. Like I will give you more examples for if at all you want for this brackets, but for now we'll concentrate on this problem. Right. So they're asking in this structure, for this structure, how many stereoisomers are existing? Go for it. If at all you are practiced, you don't even have to think about it. You can just say like that. Ah, sir, this is the answer. But now, yeah, you have to take your time, think.
sir. I didn't really draw the structures, but is the answer 8?
8. 8? No. So the options I have are 2, 4, 5, and 7. 8 is actually a very big number. Yes. Any other answers? Just apply whatever you have learned. That's it. As simple as that.
Sir, I got 2.
2. Okay. Can you explain how 2, ma'am?
Sir, I got cis and then trans.
So cis and trans for this double bond.
Yes.
Is it?
Yeah.
What about the ring structure? Just now we spoke, right? The ring structures can. That too you can see there are 2 substituents here. One chlorine, the other one is this group.
Okay, sir. Okay.
Right?
Sure. So that means it will be 4, right?
Exactly. That's it. The answer is 4. Right? So obviously cis and trans for this double bond 2, that is cis and trans, obviously you can understand what I mean. Cis and trans. This obviously is in trans, right? Right? So I can even put cis for this. So here 2, and obviously for the ring structure, again I can have 2. Totally 4. That's it. Very simple, right? Yes, everybody understood how is it 4? For the double bond 2, for the ring structure 2. That's it. Totally 4. How much time it took? If you really, and if you just really, how to apply, that's it. This kind of question will take not more than 30 seconds for you to answer. Right? So everybody understood? How is it 4?
Yes, sir.
Yes. Okay, cool. So yeah, that is about, or can I give you one more? More question if I have to give you. Okay, I think we are done. We have done enough number of questions. Yeah. Okay, cool. So yeah, people, that is about geometrical isomerism, right? So please understand that it is not only going to be in double bond. I can even have that coming in ring structures, right? Cool. Okay. So next thing what will we speak is about, you already studied it, but again, we'll just have a very quick glance of this. We're going to see optical isomerism, right? Okay, now you would have started optical isomerism in your 12th class right now in your first chapter, that is alkyl halides, aryl halides, right? Now tell me, what do you know about it? How do I determine whether a particular compound can show optical isomerism or not?
So using chirality.
Okay, yes, using chirality, but before that, they use some special type of light and all that. What is that?
Plain polarized
There
light.
is
Yes, right? So we use plain polarized light. Okay, so what do you know about plain polarized light?
Vibrates only one direction.
Good, right? So plain, anyways, don't worry, I'll anyways explain you, but just asking you how much you know. So yeah, plain polarized light is going to have vibrations only in one direction. Okay, right? So yeah, we'll directly go for it, right? So how do we determine whether that particular compound will show optical isomerism or not? Obviously, by looking at it, we can do, but this is how we generally go for the quantification, right? How much is the things, right? So anyways, so I have normal light, which is having vibrations in all three directions, right? 1, 2, and the round represents another direction, right? So all the possible directions, this is my normal light, they have their vibrations, right? So I will pass on this normal light to something called as a polarizer, right? So this polarizer is going to polarize the light, right? So the output of this is going to be this, that is the vibrations, as you said, is going to be only in one direction, and this is what is called as my PPL, plain polarized light, right? So this plain polarized light is now given to the, is made to bombard with the sample in the sense whether the compound which we are going to check whether it can show optical isomerism or not, right? So this is going to be given to the sample cell. So sample cell in the sense, this is the this is the vessel in which the sample is present, right? Okay, so this is going to be given to the sample cell, and then you are going to observe, right? So you're going to observe what happened to the light, right? So there can be three possibilities, right? So what are the possibilities? Say there would be nothing happening to the light, however it just went, it came out just like that, there is no change in the plane polarized light, or you can see that they would have rotated towards left, or they would have rotated towards right. Okay, so these three are the possibilities, right? So obviously these two are what we are interested in, correct, right? So whenever you see that the plane polarized light is rotated towards the right or towards left, then I would say that particular compound in the sample cell is optically active, right? That particular thing, that particular sample in the sample cell is optically active, and whenever you see nothing is happening to the plane polarized light, so it is going to be called as optically inactive, right? And we know what are all the notations which you're going to use, right? So whenever you see that it is rotated towards the left, I will be calling it as levorotatory, or I'll be giving a minus sign, or I'll be giving a letter L, levorotatory, right? And whenever you see that that the light is rotated towards right, right? So I'll be giving a plus sign to this, or I'll call it as D, because it is going to be called as dextrorotatory molecule, right? So all these we already know, right? Okay. Now we have to speak about the sample cell, right? So this please understand, there are going to be certain standard conditions which has to be maintained. How do I put it, right? See, what and all do you think are going to be the factors which can influence the amount of rotation? Like, see, I say that it is going to get rotated towards right or left, but how much will the rotation be will based on what and all are the factors is what I'm asking. Can you think and tell me what and all the factors which will affect? Say, assume that the compound is optically active, right? But how much rotation is going to happen? Either say 5 degrees, 10 degrees, 15 degrees. That particular number is going to based on what factors? Can you think and tell me? Did you understand my question?
Yes, sir.
Yeah. So what do you think will be the factors which will affect the amount of rotation? Obviously, the compound will definitely different compounds will have different rotation. That is okay. Other than that,
Nature of medium.
in the sense, the solvent used.
Yes, sir.
Good. Yes, definitely. Solvent. Obviously, you cannot just put the sample just like that. You have to dissolve that particular compound in a solvent and then use it. Yes, definitely, solvent makes a effect. Okay. Other than that, good.
Amplitude, sir.
Amplitude of
Light.
light used. Okay, we can take it, but not one of the main factors. Okay, accept it. Anything else? You should not say amplitude. You should say intensity or wavelength. Okay, the better way to put it is not about the amplitude. It's about the wavelength or frequency. Yes, that matters. Amplitude is just the intensity, right? So that I don't think will have much effect. But yeah, the wavelength or the frequency of the light used, yes, it does matter.
Sir,
Okay, then.
Sir, the substituent attached to the carbon atom.
Sample. You're talking about the sample?
Yes, sir.
Yeah, definitely. Sample, if I change the sample, if I put some other substituent, yes, definitely. But yeah, but that we already told, right? Definitely, if I change the sample, it's definitely the amount of rotation will change, right? What other things? Okay. So definitely, other than that, temperature plays a very good role, right? If you increase or decrease the temperature, right? So yes, that would have a drastic effect, right? Now, other than that, I can have the sample cell which which you're talking about there. That dimensions of the sample cell also matters, right? Say, how do I put it? If I have a very short cell, right? If I have a very small cell, obviously the interactions between the plane polarized light and the sample which is present there, right? So will it be? I mean, will be very short. The amount of interactions will be very less. But if I put a very big sample cell, obviously the number of interactions between the plane polarized light and the sample increases, right? So the length of the sample cell also matters. Okay, the length of the sample cell, how long the sample cell is, that is also a criteria, right? Other than that, there is one more thing, right? Now that is regarding the sample. Now again, not different compounds I'm speaking, but same compound at different concentrations, right? Say 1m, 2m, 3m, 4m. Definitely, I will have a change in the optical rotations, right? So all the factors you said, yes, accepted. Other than that, the main factor, I mean, not main factors, other factors would be the length of the sample cell, right? And the concentration of the sample cell, not sample cell, concentration of the sample, right? Also matters, obviously, and temperature. Okay. Now, so obviously we should maintain some standard things, because say for a compound X, I measure the optical rotation with 1m, right? For another compound Y, if I measure it with 2m concentration, and I want to compare how much optical rotation they have, it is stupidity. We should not do it like that, right? So all the conditions must be similar for all the compounds which you're going to measure. Okay, only then I'll be able to compare. Okay, this is more optically active, this is less optically active. All these things will be able to say, right? So we are going to fix certain things, right? And then we are going to measure, right? So what and all we are going to fix is, first is about the length of the sample cell, right? So for standard, they say specific rotation. When I say specific rotation, these are for the standard conditions, right? So what are all the standard conditions? So specific rotation, okay, fine. So you have the length of the sample cell to be 1 decimeter, right? The length of the sample should be like, I think, see, I can have questions coming from this, or I might not, but still we cannot leave just because they are little what to say, vague, but still. So the length of the sample cell must be 1 decimeter, right? And the concentration, or say, like in most of the things, like actually I do this, what is that, this plane polarized light things in labs, right? So generally we don't speak in terms of concentration, we speak in terms of density. Okay, density of the sample is what we speak, and sometimes, yeah, concentration also we use, but most of the time we use density. Okay, so the density should be how much? Oh god, wait, density, I think it's 1 gram per centimeter cube. Density should be, no, I forgot the value. Oh god, wait. Density should be, yeah, 1 gram per centimeter cube, right? So density should be 1 gram per centimeter cube, and the length of the sample cell should be 1 decimeter, right? So the, again, temperature should be 25 degrees Celsius. Temperature should, room temperature, right? Temperature should be 25 degrees Celsius. Now all these has to be maintained. Okay. Then if you measure for all the compounds, right, that is going to be called as specific optical rotation. The angle which you're going to get, right, is going to be called as specific optical rotation. Okay, right? So now if at all you don't maintain these, so sometimes what happens is, right, if you're going to measure for a particular compound, right, if you're going to measure the optical rotation with these conditions, sometimes the value will be very small, right? It is not that significant. So what will you do? Obviously you will change the length of the sample cell, you will change the density, right? So obviously now in that case it is not going to be so it is going to be called as specific rotation, right? It is going to be just called a rotation, right? But again, if you want to compare that particular compounds what is that particular compounds specific rotation with the another compound specific rotation, but in this case what happened? You didn't get the specific rotation. Why? Because you changed these conditions, right? So there is going to be a formula which is going to connect the specific rotation to the rotation value which I got. That means at different conditions, right? So I'll be able to use this formula even though I didn't use my standard conditions, but I'll be able to use that particular formula to connect the optical rotation value which I got to the specific rotation value which I'm expecting. Okay, the formula is very simple. This is how the formula is: alpha s. S talks about the specific rotation, right, which is equal to the alpha value observed, that whatever value you have observed, divided by L into D. This is the formula. Length, L is the length of the what is that, sample cell. D is the density of the sample cell. Or sometimes if at all you're not using density, use concentration where density is there. Okay, so this alpha s is the specific rotation, and alpha observed is what you observe in the non-standard conditions, divided by length of the sample cell into into the density of the sample, or say the concentration of the sample. Okay, so by this, even if you don't follow standard conditions, whatever you observe can be connected to calculate what is the specific rotation of the molecule. Cool, right? So I have seen like very rarely problems coming from this, but still, if it comes to a simple formula, you substitute and get the answer. Cool, right? Fine. So that is about all the instrumentation part of this optical activity. Now we'll move on, right? So every time I'll not be able to use these things to find out whether that particular compound is optically active or not. So as you said, just by looking at the compound, right? Just by looking at the compound, I'll be able to tell whether that particular compound is optically active or not, right? Okay, so for that only, as you said, the chiralities and those stuff, will come into the picture. Okay, fine. So as you said, yes, chirality is the condition for us to determine whether that particular compound is optically active or not. But chirality is not the only condition. What are the conditions? Tell me. For a compound to be
Asymmetric carbon.
optically. That's what is chiral carbonate, right? Other than that. Only one condition. So there are compounds where even if I have chiral carbon atoms, hope we all know what is chiral carbon atom, but still, anyways, I'll explain again. So like having chiral carbon atom is alone not sufficient, right? Even if you have chiral centers, right, the compound might be optically inactive. What could be the reason?
Mirror image.
Mirror image. That's what we said. I mean, in terms of chirality. Okay, let me ask you this question. I have this compound. Okay, right? So do I have any chiral centers here?
No, sir.
Well, okay, first basic question. What is a chiral carbon atom? Forget about this compound. Tell me, what is a chiral carbon atom? Or what do you mean by a chiral center?
If we rotate it around that center, then we will
Sorry?
if we rotate it around that center, then we'll get an exact mirror image or something.
No. So basically, when I say chiral substances, right? Forget. Okay, I will forget that you know this. Okay, fine. Right. So yeah. So when I say, so forget about chemistry, right? So when I say chiral substances, right? When I say chirality, right? So chirality means the phenomenon of non-superimposable mirror images of each other. Again, I repeat, right? When I say chiral molecules or chiral substances, that means the mirror image of that particular compound and its mirror image are not going to be superimposable to each other. Say for now, what do you mean to superimposable? Obviously, your hand is a achiral substance, right? Why? Because if I just keep my hand in the mirror, I know this particular thing, and the mirror image in that mirror will coincide exactly. Correct. Now, those kind of substances are what are called as achiral substances. They are not chiral, right? But say, for example, if I have something like W, right? W, if I'm going to go show it to the mirror image, will it? Not W. W is achiral. B. B will be a good option, right? So B, right? The letter B, if you're going to show it to the mirror and try to superimpose, they are not going to superimpose, right? So B is the chiral letter, right? So hope you understood what do you mean by chirality. Chirality means they should be non-superimposable mirror images of each other. They should not be able to superimpose. That particular compound or say that particular substance and its mirror image should not be able to superimpose. If that happens, yes, I will call that particular compound or molecule or substance or whatever it is as a chiral substance, right? So chiral, again and again I repeat, chirality means non-superimposable mirror image. This is what should come to your mind. Okay, right. Now, for in chemistry, especially in organic chemistry, right? Now, how do I determine whether that particular compound is chiral or not? That means how can I ensure that particular molecule and its mirror image is not superimposable, right? Is by looking at something called as chiral centers. Chiral centers, or it is also called as chiral carbon atoms. Okay, right? So what do you mean by a chiral carbon atom is the question, right? So obviously that particular chiral carbon atom and its mirror image are not going to be superimposable. That I understood, right? But it is not like, okay, that is the general definition. But what exactly is the definition is, so chiral carbon atom is one, right? A chiral carbon atom is one which has all four groups attached to it to be different. Okay, all the four groups attached to it to be different. Say now I know that obviously each carbon atom will have four groups, tetrahedral geometry, right? Okay, so this all we know, right? So the four groups attached to this carbon atom, if and all these groups are different, say I have four different groups, A, B, C, D, there are four different groups attached, right? Now this particular carbon atom is what is called as your chiral carbon atom, right? Or it is also called as chiral center. Okay, now everybody understood what do you mean by a chiral carbon atom, right? So for a chiral carbon atom, the four groups attached should be different. I'm not talking about the atoms, right? It can be two carbon atoms also. Say for example, I can put a methyl group and I can put the ethyl group, and definitely these two are different groups. You should not say that sir both are carbon atoms attached. Then it is same. It is not chiral. No, it is not about the atoms attached. It is about the groups attached. Two different groups. This is methyl group. This is ethyl group, right? So, and obviously all the other two also matter. Say for example, I can put a OH, I can put a Cl, right? So now what do you see? All the four groups are different, right? So this particular carbon atom which is here is what is called as your chiral carbon atom. Is that okay? Okay. Now this is the first condition. So for the conditions for optical activity, right? What are the conditions for a particular organic compound to be optically active? That means what is the condition that it will rotate the plane polarized light either towards right or towards left? Is the first condition is at least one chiral center, right? At least one chiral carbon atom should be there. But again, I can have exceptions. Okay, this is the general rule, but I will show you at the end of this optical isomerism that even though some compounds do not have optical chiral center, they can be optically active. That we'll see later. Only 2 or 3 compounds are going to be like that. Okay, but generally I should at least require one chiral carbon atom to be present for the compound to be optically active. Is that okay? Right. But again, this is not the necessarily condition. Second condition is also there. The second condition is there should not be any planes of symmetry. Right? The molecule should not be symmetric. Okay. So the first condition is they should have a chiral center, at least one chiral center, right? And the second condition is their molecule should not be symmetric. Okay, you hope you know what is symmetry. If I cut at one point, this side and this side are going to be similar, right? That should not happen. Okay, so if these two conditions are satisfied, yes, the molecule will be optically active. Okay, right? Now, if see, and you don't have to look into this. The second point, like you don't have to look into the plane of symmetry if you have only one chiral center. Okay, if you have only one chiral carbon atom in the whole molecule, there is only one chiral carbon atom. Okay, then you can just close your eyes and say that molecule is going to be optically active. The problem comes, right? The problem comes when I have more than one chiral center. Okay, so then only you have to look at this plane of symmetry. Okay, you can even make a note of it somewhere. This number of plane of symmetry should be looked into the picture. I mean, it should be brought into the picture only if you have more than one chiral center. If you have only one chiral center, you can just close your eyes and say that that molecule is definitely going to be optically active. Okay, right? So yeah, these two conditions, and obviously for this, even if there are no chiral centers, that certain molecules can be optically active. That we'll see later. But for now, these two are the conditions. Is that okay? Right? Cool. Now we'll take some examples. Okay, fine. So people, there are so many, what to say, how to put it. So to check whether that particular compound is optically active or not, obviously these two are the conditions, right? But certain times what happens is one of the stereoisomer will be optically active and the other stereoisomer might not be optically active. There can be certain ulta-pulta things happening like that, right? So for all those, right? So there is one type of notations how to represent that particular molecule. There is a special way of representation. Okay. Now that is actually going to help us a lot. Okay. So that is what is called as your Fisher's formula, or it is also called as Fisher's projection formula. Okay. Now what are we going to do? Right. So we know that each and every carbon atom is going to be tetrahedral. That means it is going to have a 3D shape. Correct. One bond is coming towards you, one bond is going away from you, two more bonds are in the same plane. Right. So what to say? Working with those kind of structures is a little difficult. Okay. So what do we do is that we will try to convert the 3D structure into a 2D structure. Okay, we'll try to convert the 2D structure into a 3D structure into a 2D structure, and that 2D structure is what is my Fisher's formula. Okay, so it just uses two things, right? So Fisher's formula uses my vertical lines and horizontal lines. Very simple. Okay, vertical lines and horizontal lines is what is going to get used, right? And obviously you see that there is a meeting point for your what is that? For the vertical and horizontal lines, the meeting point is here, right? Now this meeting point represents the chiral center, right? This meeting point represents the chiral center. Okay, so if at all you have only one chiral center, then only one meeting point. If at all you have two chiral centers, then you have to make it like this. There should be two chiral centers, means two meeting points of first chiral center, second chiral center, right? So like this, we'll be using the formulas. Now, how do you convert it? Okay, we understood that I'm going to have vertical lines and horizontal lines, and I'm going to have the meeting point representing the chiral centers. Okay, right? So if I give you a structure, 3D structure, how will you convert it? Very simple. I'll tell you, right? So whenever you see bonds pointing up and away, it should be in vertical position. Right, whenever you see bonds pointing up or away, it should be in vertical position. And whenever you see bonds pointing down or towards you, it should be in the horizontal position. Once again, okay, horizontal positions, right? So up and away, vertical, down and towards you, horizontal positions. Let me take an example. Right. So say I have hydrogen, OH, say Cl, and say Br. Okay. So I have this particular molecule with me. Now I have to represent this molecule 3D structure into this form, Fisher's formula. Right. So now how will I do it? So I can easily say that there is one chiral center because there is there is what is that, 4 different groups, right? So I will make a meeting point. Done, right? So what I said to you, up and away should be in vertical position. So up, I have a hydrogen, right? And away from me is Br, right? So both my H and Br should be in vertical positions, right? So obviously H and Br should be in vertical positions. No problem. Okay. Now I have Cl pointing down Obviously, you're seeing it, right? Cl is pointing down in the same plane, right? Okay. Now, please understand this up or down. These two bonds should be in the same plane. Obviously, the away or towards you will not be in the same plane. That we understood, right? So the up or down pointing towards you, it was speaking for the bonds which are in the same plane as the board or as your paper which you're writing, right? Okay. So what I'm telling, so yeah, so see H and BR. H is pointing up and BR is pointing. Oh, am I doing any mistake?
Sir, BR is pointing towards us.
Exactly, right? So yeah, it's wrong. So we're just pointing away from me. OH is pointing away from me. So OH should come here. Right? So yeah, so H is pointing up and OH is pointing away from me. So up and away in the vertical position. Right? And what is left out? Cl is pointing down and Br is pointing towards you. So down or towards you in the horizontal positions. So you can put Cl and Br. And this is exactly how I represent this 3D molecule in terms of Fisher's formula. Okay, right? Now this is easier to work with, right? You can just see. This is very easier to work with. And this is also like, okay, the main reason of why we are doing this is because I can easily get the mirror image of this. Is it not? Getting a mirror image of this is a little complex, but this I can easily get a mirror image, isn't it? Say very easily I can put, if I put a mirror here, obviously I'll get Br here, right? I will get Cl here, I'll get H here, I'll get OH here. So easily I'll be able to draw the mirror image, right? So that's the main reason why we go for Fisher's formula. It is easier to work with 2D structures rather than 3D structures. Okay, right? So this I want to tell you. Okay, right? Fine. Well, moving on. Any doubts till now, people? Any doubts where you want to ask this, that?
Can you explain that drawing again, sir? I didn't get it, the up and away.
Sure. Right. So the thing is, using in Fisher's formula, we are going to convert a 3D structure. Obviously, we know in the 3D means I have wedge, dash, all these things are there. So I am going to convert that into 2D formula. Right? That is in 2D structure. Right. So in that structure, we have only two things or three things, I would say. One is the vertical line, another is a horizontal line, and there is a meeting point. Okay. So vertical and horizontal lines are basically going to represent the bonds, right? And the meeting point represents the chiral carbon atom, right? As many as chiral carbon atoms you have, as many as meeting points you should have. So in this case, I have only one chiral carbon atom, so there is only one meeting point, right? But if at all there are two chiral carbon atoms like this, we have to write, right? Like this, you have to draw a structure. So this is first chiral center, this is second chiral center. Okay, this is understood. Now, which bonds you have to put where? You have two positions. One is vertical positions in the Fisher's formula, and you have horizontal positions in the Fisher's formula, right? So for that only I told you, if you find that bonds are pointing up or away from you, you put it in the vertical position. And if you find that the bonds are pointing down and towards you, so last case it is up and away. In this case, it is down and towards you. Then you put it in the horizontal positions, right? Now that's where I give you the example. Now, if you look at this example, hydrogen atom is pointing up, is it not? Right? So hydrogen atom pointing up, and what else? I should look for away, which is pointing away, and that is OH. OH is pointing away from me. So H up and away should be in vertical position. So H and OH, H is pointing up, OH is pointing away from me. So that came in the vertical positions. Okay, next. Down or towards you in horizontal. Okay, down is this. Cl is pointing down in the same plane, right? And what is pointing towards you? That is Br. Br is pointing towards you, correct? So down or towards you in the horizontal position. So Cl is pointing down, Br is pointing towards you. So this is the Fisher's formula. Is it okay?
Yes, sir. Thank you.
Okay. So yeah, very simple. We'll take more examples. Don't worry. Right? Cool. Right. So we are going to see three things now. Okay. So three things are this enantiomers, diastereomers, and I have something called as mesomers. Okay, enantiomers, diastereomers, and mesomers. Right. Okay. Now we have to understand what are all these three important terms and with respect to optical isomerism. Right. Okay. So we'll take down definitions first for enantiomers. Please take down the definition. I'm giving you the definition for enantiomers. Right. So they are stereoisomers. Enantiomers are stereoisomers which are non-superimposable, mirror images, which are non-superimposable mirror images of each other. Right? So enantiomers are stereoisomers. They are stereoisomers. They have different orientations of bonds in 3D space, right? But what is the condition? They are stereoisomers which are non-superimposable mirror images of each other. They should not be able to superimpose. Okay, so that means what? I'm just talking about the optical activity, optically active compounds, right? So obviously, with optically active compounds, their mirror images are what are called as your enantiomers. If you put it in proper definitions, they are stereoisomers which are non-superimposable mirror images of each other. Right. So if a last compound which we saw, right, we saw 4 different groups and its mirror image, right? So those two are together going to be called as enantiomers. Is that okay? Right. Next, diastereomers. Please take down the definition. We already know, right? We the last class, what we said about diastereomers?
All geometrical isomers are diastereomers.
Exactly, right? All geometrical isomers are diastereomers. Like if the exact definition comes like this, please take down the definition for diastereomers. Right. They are stereoisomers. They are also stereoisomers, obviously. Right? They are stereoisomers which doesn't have any mirror image relationships. Any mirror image relationships. Okay. Don't worry, I'll give you examples for all of them. Right. Let's take on the definitions now. Right. Next, mesomers. Mesomers definition. It's exactly opposite of enantiomers. They are non-superimposable. They are superimposable mirror images. Okay. So just take down. For mesomers, they are stereoisomers. They are stereoisomers which are superimposable mirror images of each other. Exactly opposite of enantiomers. Right? They are superimposable mirror images of each other. Right? Okay. Right. Now we will take some examples. We know enantiomers. Enantiomers just now we saw. They are like if I have only one chiral center, definitely that and the mirror image will not be able to superimpose, right? So diastereomers, I'm telling you that they don't have any mirror image relationship. And what do you mean they don't have mirror image relationship? They are not just connected, they are just stereoisomers. Like how do you have geometric isomer? Do you speak of anything about in terms of mirrors there? No, just the 3D orientations are different, right? So that is for your diastereomers. And for mesomers, right, I said that they are superimposable mirror images. Okay, so what I mean by them is, say they have chiral center. I told you, right, even though sometimes you have chiral centers, obviously more than one chiral center, I told you that some compounds can be optically inactive, right? And why they are optically inactive? Because they have a plane of symmetry, right? So for mesomers, I can tell you one thing for sure: they might have chiral centers. Yes, they will have chiral centers. Definitely more than one chiral center, right? More than one chiral center. But the thing is, they have at least one plane of symmetry. At least one plane of symmetry. Okay, that makes it superimpose. That makes the mirror image and the compound to superimpose with each other, and thereby overall optically inactive. Overall optically inactive. Mesomers are optically inactive. They will not rotate plane polarized light, even though they have chiral centers. Okay, so fine. So these are all the common definitions you have to know. Now we'll take some examples. Okay. Okay. So let me take 2,3 dichloro pentane. Can I take? Yeah, pentane. I'll take. Right. I have 2,3 dichloro pentane. Okay. So let me draw the normal structure first. Then we'll go for the Fisher's formula. Okay. So I know how it looks. CH3, CHCl, CHCl, CH2, CH3. Right? Okay. Now tell me how many chiral centers I have in this molecule.
So 2.
Yes, 2. Right? So obviously I can say this is a chiral center. Why this is a chiral center? H, Cl, CH3, other group. All 4 groups are different. Right? Okay. Now this is again a chiral center. H, Cl, one group, another group. Definitely all 4 groups are different. So I have 2 chiral centers. Right? Do I have any plane of symmetry? No, definitely not. Right? There is no plane of symmetry here. So this compound is definitely going to be optically active. Okay. So please understand, there are going to be so many stereoisomers. See, when I say stereoisomers, just the orientations of bonds in 3D space is different. Just that, right? So there are going to be stereoisomers which are going to be enantiomers. There are going to be stereoisomers which are going to be diastereomers. And definitely I cannot expect mesomers here because there is no plane of symmetry. Okay, so I can expect either, I can expect 2, that is enantiomers and diastereomers. Now, how are we going to do about it? We are going to convert this particular structure into Fisher's formula. Okay, now sir, you can ask me, sir, you said 3D structures to 2D structures. This is already in 2D. Now, how do we convert it? Very simple, right? So whenever you see this alkyl chain, main chain, right, alkyl chain, main chain, this main chain should continue along the vertical line. Okay, so if I just draw, you will understand. And all the other branches, if you have any branches, say for example, fluorine is a branch here, so that should come along the horizontal positions. Okay, so again I repeat, the whatever the chain goes, that entire path will come in the vertical position, right? And the branches will come along horizontal position. Okay, very simple, right? So let me draw it. So yeah, so there are 2 chiral centers. So I have to make 2 meeting points between the horizontal and vertical lines. And obviously you start with CH3. Now what do you have? You basically have C2H5. CH2, CH3 is what you have, right? So please understand, for this chiral center, For this chiral center, I have basically, this is a group. And what is this group? This group is ethyl group. And I directly wrote it as C2H5. You can even, if you want, you can write it as C2CH3, CH2CH3 also. No issues. Okay. So I hope you understood when I said that the alkyl chain, that path should be coming in the vertical line. That's exactly what I did. Right. Now I have to put in these, the 4 questions has to be filled with hydrogen and chlorine. Is it not? See, you can account for this carbon atom CH3. These 2 are also accounted for. The ethyl group is also accounted for. The only thing which I have to account for is these 2 hydrogens and chlorines. Right? Now, you can put it anywhere you want. Okay? So first, I can put, say, hydrogen, chlorine, hydrogen, chlorine. This is one of the possibilities I can put. Right? Okay. Now, let me draw the mirror image of this. Okay, let me draw the mirror image of this. If you try to draw the mirror image, how will you get? Say now Cl will be here, Cl will be here, H will be here, H will be here, CH3 and C2H5. No issues, right? So let me mark the structures as 1 and 2. Okay, right? So now tell me, if I try to superimpose 2 onto 1, will it superimpose?
Yes, sir.
How? How will it superimpose? I take it, I place it here. Will it superimpose? No, right? Obviously, you see that the chlorine atom will come here. Is it not? This chlorine atom is what I have, right? If I try to superimpose, they will come here along with hydrogen. So maybe you can tell CH3 and C2H5 are superimposing. But what about hydrogens and chlorine? They will not superimpose, right? So definitely 1 and 2, as the definition tells you, are non-superimposable mirror images, right? So how am I going to call 1 and 2?
Enantiomers.
Exactly, right? So 1 and 2 are going to be non-superimposable mirror images of each other. So 1 and 2 are going to be called as enantiomers.
Sir,
Okay.
I have a doubt.
Yeah.
So what if you rotate the second molecule through 180 degree and then superimpose?
Correct. Accepted. So the thing is, if I rotate it through 90 degrees and if I'm able to superimpose, now they are not enantiomers. But if I rotate them through 180 degree and they are superimposing, no, they are not. They are not enantiomers. I know it is confusing, but I have a better method of doing it. I'm just explaining you. There is going to be a trick. I'm going to give you the trick, right? With that trick, you will be able to find whether they are enantiomers or mesomers or diastereomers. So wait for it. Yeah, it's a good question. Definitely, if I rotate them by 180 degrees, they will superimpose. But there is a rule which says that if you rotate them by 180 degree and they superimpose, they are not. They are still enantiomers. Okay, but don't worry. All your questions are really valid, right? But I am going to give you a trick, right? There is going to be certain things which you can do. By that, I'll be able to identify whether that compound, these 2 are enantiomers, or diastereomers, or mesomers. Okay, does that answer your question?
Yes, sir. Yes, sir.
Okay, right, cool. So yeah, they are enantiomers. Okay, now we'll take for the same compound, right? For the same compound, right? I can now this is one of the stereoisomer and its mirror image is there, right? Now I can even draw something like this, right? So instead of putting both hydrogens and both chlorine on same side, I can even put it like this. Say 1 is like this, and I'm putting Cl and H like this, right? So now let me call it as 3. It's not 1. Let me call it as 3. Another stereoisomer. And definitely the mirror image will not be the same. Mirror image will also change, right? So the mirror image, in this case, I'll get Cl and H. And yeah, this is fine. And here I'll be getting Cl. No issues, right? Okay, now tell me, will they superimpose? Now again, I'll call it as 4. Right? So if I trick it and try to paste it here, will they superimpose?
No, sir.
No, right? So again, 3 and 4 are enantiomers. No problem, because they are non-superimposable mirror images of each other. Now my question is, What about 1 and 3? What about that pair? How do you call them? Or say 1 and 4, or 2 and 3, or 2 and 4. Like I'll just make list of them. So 2 and 3, and 1 and 4, and 2 and 4, all these pairs. What are you going to call them?
Diastereomers.
Exactly, right. So what do you see? They are just stereoisomers, though they do not have any mirror image relationship, right? Just that the sorry. So just that the orientations of bonds are different, right? So 1, 3, 2, 3, 1, 4, 2, 4, these pairs are going to be called as diastereomers. Okay, right? So now you understood what do you mean by diastereomers. They are just stereoisomers. That's it. No mirror image relationship, right? But when you have mirror image relationship, that is when they are non-superimposable, they are going to be called as enantiomers, and when they are superimposable, they are going to be called as mesomers. Right? Okay. Right. So that we understood. I just wanted to give you the difference between enantiomers and mesomers. Sorry, enantiomers and diastereomers. And obviously mesomers, you know how to check it. I'll give you the example. Right. Right. So if I take the first compound which I started optical isomerism, say if I now if you look at this, do I have chiral centers?
Yes,
If
sir.
yes, how many? How many?
2.
Exactly, right? 2. So these 2 are my chiral centers. Correct? H, OH, CH3, other group. Same way. H, OH, CH3, other group. Right? So I have 2 chiral centers, but what should I look for? This
Plane of
compound is
symmetry.
optically inactive.
Plane of symmetry.
Correct, right? So definitely I have a plane of symmetry here. You can see that that side and this side are exactly same. So definitely this compound, one of the stereoisomers, the pair, one of the pairs would be mesomers. Okay, fine. So yeah, that's about mesomers. Okay, so guys, as I told you, I'm going to give you a trick. What is the time? Will I be able to complete? Okay, fine. So like that, we'll see that trick later. Okay, whether how to find out whether that is not later, next class, right? But I can tell you how to find the number of stereoisomers. There is a formula. There's again a trick, right? So I'm going to give you the trick. Say now if you have only 2 chiral centers, it's very easy. Say what if I have 10 chiral centers, right? So you now they can even ask you to calculate how many enantiomers, how many mesomers, totally how many stereoisomers, all these can be asked. Okay, so that formula I'm going to give you now, right? How to find the number of stereoisomers. Okay, so first for that, case 1, right? So when n is even, what do you mean by n? N is the number of chiral centers. N is the number of chiral centers. Okay. Now n, number of chiral centers when n is even and there is no plane of symmetry. Right? There is no plane of, this is the first case, right? So case 1, n is even, that is that the number of chiral centers is an even number, say 2 or 4 or 6 or something like that, and there is no plane of symmetry. Okay. So in that case, total stereoisomers, total number of stereoisomers will be equal to 2 power n minus 1. Very simple, right? 2 power n minus 2 power n minus 1 or 2 power n. One second, people. Just a moment. Where is the book? So yeah, so case 1, okay, so number, we can write it like number of optically active stereoisomers, right, would be 2 power n, okay, right, and the number of mesomers would definitely be 0, is it not, because there is no planar symmetry. This is the first case, right? So case 1, when the number of chiral centers is even and there is no planar symmetry, it is the total number of optically active stereoisomers are going to be 2 power n. Okay, next. Oh, so you can, okay, so n is even or odd in this case, no problem. Okay, so n is even or odd, but there should not be any planar symmetry. Then you can directly tell that it is going to be 2 power n, right? Okay, now case 2. When n is say even and there is planar symmetry, right? Now there is planar symmetry. Okay, so the number of optically active stereoisomers would be 2 power n minus 1, right? And number of optically inactive, that is my mesomers, right? Optically inactive stereoisomers, which are nothing but number of mesomers, would be 2 power n by 2 minus 1, 2 power n by 2 minus 1 in powers. Okay, and obviously if they ask you total number of stereoisomers, if they ask you total number of stereoisomers, it should be sum of them, right? 2 power n minus 1 plus 2 power n by 2 minus 1, that is the total number of stereoisomers. Optically active or inactive doesn't matter. If they ask you number of optically active alone, use that formula. Number of optically inactive alone, use this formula. Total number, sum them up. Okay, so that is case 2 when n is even. This is for n is even. First case n is even or odd, but there is no planar symmetry. In this case, I have a planar symmetry, at least one planar symmetry, right? Now, last case. Case 3, n is odd and there is planar symmetry. Right? So in that case, number of optically active stereoisomers would be 2 power n minus 1. That is same, but the number of optically inactive stereoisomers would be 2 power n minus 1 by 2. Yeah, correct. 2 power n minus 1 by 2. Again, total number of them would be this plus that. Okay. Okay. So that's about the different. So if you have only 1 or 2 chiral centers, easily you can do. But if you have more than 2, like 5 or 6 or 7, at that time, you can just put the molecule in either of these cases. We just look for whether they have a planar symmetry or not, and look for the number of chiral centers, whether it's odd or even, and you can usually guess, not guess, you can exactly get the answer for the number of optically active stereoisomers and number of optically inactive stereoisomers. Is that okay? Right? So next class I'll be giving you the trick to find out whether that particular pair is an enantiomer or diastereomer or mesomer, and then we'll go on to see molecules which doesn't have a chiral center but still are optically active. Those kind of compounds we'll see. So what is the time? Yeah, I think if you do you have any doubts? Any questions? Okay. Yes.
No, sir, no doubt.
Okay, fine then. So that's about for today, people. Right? So next class, we'll see. Right? Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Thank you.